Welcome dear learners. We are continuing Unit 1 Chemistry as a Science Discipline and Scientific Analysis. In the present module, we are focusing on coefficient of variation and variance in analytical chemistry. In this module, we are discussing standard deviation SD, relative standard deviation RSD, coefficient of variation CV, variance, confidence limits and problems based on these concepts. First of all, standard deviation. In the previous module, we just heard about the definition, equation and some numerical problems associated with the standard deviation. Here we are just taking for recalling the concept of standard deviation. Standard deviation in analytical chemistry is one of the most common statistical terms employed, and it is mainly used to describe the analytical data associated with the quantitative chemical analysis. The standard deviation of a population of observations is highly significant in analytical chemistry. The standard deviation measures the spread of variability of a set of data around the mean. Standard deviation is particularly useful in determining the precision and reliability of experimental results. It helps to evaluate how closely repeated measurements are clustered around the mean. Lower standard deviation indicates higher precision. You are familiar with the concept of accuracy and precision. Precision represents repeatability of results in repeated measurements. Large deviation from the mean may indicate experimental errors or outliers, which can then be investigated further. Population and sample standard deviation. You just heard about these two types of standard deviations in the previous module, and there are two important categories of standard deviations, and such standard deviations are: first one, population standard deviation sigma, and sample standard deviation abbreviated as S. However, both of these type of standard deviation measure the degree of dispersion in a set of data. Formulae of standard deviation. You know that there are two kinds of standard deviation. They are nothing but the population standard deviation and sample standard deviation. These are the formula. First of all, population standard deviation sigma is represented by the equation sigma is equal to under root sigma xi minus mu square divided by n. Here mu represents the population mean. And the second kind of standard deviation, that is nothing but sample standard deviation, which is abbreviated as S, and S is equal to under root sigma xi minus s bar square divided by n minus 1. You should note the fact that the denominator here is n minus 1. If you are having n set of measurements, for calculating the sample standard deviation, we have to use n minus 1 in the denominator. Moreover, x bar represents the sample mean. So, these are the formulae of two kinds of standard deviation that we just learned earlier in the previous modules. Now, what are the applications of standard deviation in analytical chemistry? Whenever we are discussing such applications, these are to be mentioned in your mind and keep in your mind. And the first one is, the standard deviation is a very good comparison method. You can also use the standard deviation for comparing various analytical methods. Standard deviation is highly helpful to compare the precision of different analytical methods. And the second application is associated with the determination of error propagation. When combining multiple measurements, the standard deviation helps it to estimate the overall uncertainty of results. Now, another application is associated with the reporting of uncertainty. You know that every quantitative analysis is associated with some sort of uncertainty. Analytical results are often reported as mean plus or minus standard deviation, it providing insight into data reliability. Finally, repeatability studies can also be performed by using standard deviation. When conducting repeatability test, standard deviation indicates how consistent results are under identical conditions. Hence, the concept of statistical procedure standard deviation is highly significant as far as quantitative chemical analysis and analytical chemistry is concerned. Now, we are discussing the second statistical procedure of this module, that is nothing but relative standard deviation. Relative standard deviation is abbreviated as RSD. The relative standard deviation is another way of expressing the precision, that is you can check repeatability of measurements with the help of relative standard deviation. It is particularly useful in analytical chemistry for comparing the precision of different data set, especially when their mean differ significantly. Now, the relative standard deviation or RSD is the ratio of standard deviation to mean, that is, to get relative standard deviation of a set of measurements, you have to divide standard deviation with the mean. That is, RSD can be calculated as RSD equal to SD divided by X bar. Here SD stands for standard deviation and X bar represents mean of a set of measurements. So, to get RSD, you have to divide standard deviation with the mean of the measurements. Now, another statistical procedure in which we are using in analytical chemistry is nothing but the coefficient of variation. Coefficient of variation is abbreviated as CV. The coefficient of variation CV is a statistical parameter widely used in analytical chemistry to assess the precision or reproducibility of a set of data. And the coefficient of variation expresses degree of variability relative to the mean of the data set. The CV is typically represented as a percentage, making it dimensionless and allowing easy comparison between data sets regardless of their units or magnitude. This point is very important as far as the analytical procedure CV is concerned. It is dimensionless or unitless. Now, coefficient of variation is the RSD percentage. We heard about relative standard deviation, that is equal to SD divided by X bar. When that relative standard deviation is expressed as a percentage, that is known as the coefficient of variation CV, or simply we can arrive at the conclusion that coefficient of variation CV is the RSD percentage. That is, RSD is expressed as a percentage, it is known as CV. So, you can write the expression for CV as CV is equal to SD divided by X bar, that is this part, the first part represents relative standard deviation, just to multiply with the 100 to get to the coefficient of variation. So, coefficient of variation is RSD percentage. Now, we are going to illustrate the calculation of coefficient of variation with the help of an example. Suppose a laboratory measures the concentration of a compound in a sample 5 times and the data obtained are shown here. The concentration is in the unit of milligram per liter and the data are 98, 100, 102, 99 and 101 milligram per liter, and we are going to evaluate the coefficient of variation of this set of data. And to evaluate the coefficient of variation, we have to proceed through different steps. And the first step is the calculation of the mean. You know how to calculate the mean of the values. Here there are 5 values. You have to add these values together and divide these total with the total number of measurement, that is equal to 5. So, mean of the present data, present set of data is equal to 100. Now, in the second step, we can calculate the standard deviation. The standard deviation is simply the sample standard deviation. That is why we are using n-1 in the denominator. So, SD is calculated as standard deviation is calculated by using this expression SD equal to under root xi minus mu square divided by n minus 1, and for this data SD is equal to 1.58 milligram, and you know the standard deviation of the set of data is equal to 1.58 milligram per liter. So, you have to calculate the standard deviation, and the standard deviation calculated should be the sample standard deviation, and if you are having n measurement, in order to calculate the sample standard deviation, you have to use n minus 1 in the denominator. So, in the present problem you are having 5 data and n minus 1 is equal to 4. On using this equation, you will get the standard deviation value as 1.58 milligram per liter. Now, in the third step, we can calculate the coefficient of variation. Coefficient of variation is simply RSD percentage. So, first of all, we have to get the RSD value. In order to get the RSD value, you have to divide standard deviation with the x bar. That is, standard deviation is equal to 1.58 and S bar is previously calculated, that is mean is previously calculated, it is equal to 100. So, 1.58 divided by 100, and the first part, this part represents relative standard deviation. You have to again multiply with the 100 to get RSD percentage. RSD percentage equal to CV. So, 100 cancels and the final result is 1.58 percentage. So, coefficient of variation with the given set of data is equal to 1.58 percentage. Now, interpretation of the coefficient of variation. This is very important as far as the result is concerned. So, whenever you will get a coefficient of variation value, you have to interpret it, and in the coming slides we are discussing how the interpretation of coefficient of variation should be done. Low CV value indicate less variability relative to the mean, meaning the method or instrument is highly precise. So, for a measurement to be very precise, or for an experimental measurement to be more precise, it should be associated with the low value of coefficient of variation, and high value of coefficient of variation indicate greater variability, suggesting lower precision and potentially a need for method optimization. That is, in such cases, whenever you are getting high coefficient of variation value, you have to optimize the adopted procedure, otherwise the result will not be accurate as well as precise. Now, we are discussing another statistical procedure, that is variance. In analytical chemistry, variance is a statistical measure that quantifies degree of dispersion or spread in a set of measured data. It is especially important in assessing the reliability, precision and reproducibility of analytical methods and measurements. Variance is simply the square of standard deviation. That is, variance is notated as S square, where S is sample standard deviation. Population variance is sigma square. It is the square of population standard deviation. And sample variance is S square. It is the square of sample standard deviation. You know simply the fact that variance is the square of standard deviation. You learned the fact that there are two kinds of standard deviation. They are population standard deviation and sample standard deviation. So, there are similarly two kinds of variance also. The first variance is population variance. It is the square of population standard deviation. So, population variance sigma square is equal to 1 by n into sigma xi minus mu square. Sample variance is the second type of variance, and it is the square of sample standard deviation. We know about the expression of sample standard deviation. Take the square of which gives us the sample variance S square. That is, S square is equal to 1 minus n into sigma xi minus S bar square. In chemistry, where the number of measurements are comparatively less, we are commonly using the sample standard deviation for standard deviation purpose and sample variance for variance purpose. Now, we are going to illustrate the concept of variance with an example. You imagine the situation where a chemist measures the concentration of a solute in a solution using spectroscopy. After performing 5 replicate measurements, the concentration recorded are here 9.8, 10.0, 10.2, 10.1 and 9.9 ppm. You know about the term ppm, it is parts per million, it is used to express the very low concentration terms, and we have to calculate variance associated with the data set given here. And in the first step, we have to calculate the mean or average. In order to get the mean, you have to sum all these values and divide with the total number of measurement, that is equal to 5. So, the mean value in the present data set is equal to 10.0 parts per million. In the second step, we can calculate the variance. See, the variance shown here is a square. So, it is square of sample standard deviation. So, this variance calculated is called sample variance. The sample variance can be calculated by using the expression 1 by n minus 1 into sigma xi minus s bar square. So, by putting these values of the data x bar and xi, that is individual measurement, and n minus 1, that is the total number of measurements minus 1, you can calculate the value of variance as 0.02 parts per million square. So, the sample variance in the present problem is equal to 0.02 parts per million square. This low variance indicates high precision of this analysis. That means, the value obtained is comparatively low, and that gives us an interpretation that the procedure adopted is associated with high precision, or it is a good, comparatively good analysis. Now, variance is a measure of precision. A low variance indicates high precision. The measurements are very closely grouped, while a high variance show low precision, measurements are spread out. So, this second point is very, very important, and it signifies the statistical procedure of calculating variance. Minimizing variance is very important as far as analytical procedures in quantitative chemical analysis are concerned. These are some steps to minimize the variance. Optimize and standardize the analytical procedure is the first method. In the second method, we can make calibration, that is regularly calibrate your instruments is another way to minimize variance. Use high purity reagents and consistent sample preparation techniques, this is another method, and perform replicate measurements to reduce the effect of random errors. Another part of this module is confidence limits, and first of all, we have to consider what do you mean by the term confidence limit. There is an associated term called confidence interval. All these things are highly important as far as interpretation of the data, interpretation of the results, statistical procedures, etc. are concerned. So, first of all, we are considering confidence limit. In analytical chemistry, confidence limits are used to define a range within which the true value of a measurement or a parameter is expected to lie with a specified level of confidence. A confidence interval is highly related to confidence limit. A confidence interval provides a range of values around the measured mean, that is x bar, which is likely to contain the true value mu with a given probability. The confidence interval is given by the mathematical expression Ci is equal to x bar plus or minus t into s divided by root n. Here t represents critical value. This critical value is obtained from students' t distribution table. There is a standard t table. I will shown to you in coming slides about the t table. this is a standardized data which is known as the students T table. We have to take a critical T value from the students table that I will show to you in the coming slides, and T is there. The value of T can be obtained from the table. There is an associated table, we will discuss it soon. And the second term, S represents the sample standard deviation, and simply N represents number of measurements. So, you have to keep the expression for confidence interval. That expression is CI or confidence interval equal to x bar plus or minus T into S divided by root N. Now, the confidence level is the percentage likelihood that the confidence interval contains the true value. Common confidence level in analytical measurements are shown here. 90% confidence level indicates less stringent analysis. 95% represents most common, it is most commonly used in analytical chemistry, and 99% is for highly stringent requirements. So, in analytical chemistry and quantitative chemical analysis, there are three kind of confidence levels, maybe 90%, maybe 95% and maybe 99%, and in general common analysis we are taking 95% confidence level. We are now illustrating the concept of confidence level with a small example. A 95% confidence level means that if the same experiment were repeated many times, 95% of the calculated confident interval would contain the true value. This is the most crucial information associated with 95% confidence level. If I change this confidence level to 99, I can read like this. A 99% confidence level means that if the same experiment were repeated many times, 99% of the calculated confidence interval would contain the true value. Now, a practical example to illustrate the concept of confidence interval is here. Suppose a chemist measures the concentration of a solute in a solution, and he performed analysis 5 times yielding the following results, and the concentration is in the unit of ppm. Let the obtained values are 9.8, 10.0, 9.9, 10.1 and the final value is 9.8. And we have to obtain the concept of confidence level. We have to illustrate the concept of confidence interval, and for this first of all I have to calculate the mean of the set of measurement. In order to get to the mean, you have to sum all these values and divide with the total number, and on performing that you will get a mean as 9.92 parts per million. Now, calculate standard deviation, that is simply the sample standard deviation. The sample standard deviation is equal to under root sigma xi minus s bar square divided by n minus 1. On calculating by proper substitution, we will get the sample standard deviation is equal to 0.12 parts per million. Now, in the third step, we have to find the T value from the students table. I already mentioned the fact that in order to get to the confidence interval, you have to use a T value. In order to use a T value, you have to adopt it from a standard table similar to logarithm table like that, and a table called students T table, and from that you can take the value for the corresponding measurement and find the T value for 95% confidence. In many cases we are taking 95% as the confidence level, and you have to pick the T value from the students T table for 95% confidence, and you know in the present problem n minus 1 is equal to 4. N minus 1 is taken as degrees of freedom. So, in order to pick the corresponding T value, you have to keep 2 things in your mind. What is the confidence level? In the present problem, the confidence level is 95%. And the next one is the degrees of freedom, that is equal to n minus 1. So, in the T table, there is an arrangement, there are so many values, and the values are given in the t table in such a way that degrees of freedom is on one side and percentage of confidence or confidence level is on other side. So, you have to pick apt t value from the students table that I will illustrate with the help of the coming students t table. And you should note the fact that in the present problem n minus 1, that is taken as the degrees of freedom. Here you took 5 measurements. So, 5 minus 1 is the degrees of freedom and degrees of freedom is equal to 4. So, before proceeding to the students table, you have to keep two things in your mind. The confidence level is fixed as 95% and the degrees of freedom is fixed as 4. So, now you can look this table. This is students t table. This is called two-tailed students t table. Two-tailed analysis is associated with analytical chemistry that you can study in your higher classes whenever we are discussing more things about analytical chemistry. On looking this chart, you can see the degrees of freedom in the first column. Degrees of freedom may be 1, 2, 3, etc. up to 10 is shown here. Higher numbers are also possible, and you should keep the fact that n minus 1 is the degrees of freedom. N minus 1 is equal to 4 in the present problem. So, you have to fix 4 as the degrees of freedom, and the 3 confidence level most commonly used are shown here: 90%, 95% and 99%. In the present problem, we fix it as 95% confidence level, and confidence level is 95% and the degrees of freedom is equal to 4. So, you have to take the corresponding t value. In order to pick the corresponding t value, fix the degrees of freedom as 4, look on to 95%. So, this value 2.776 is the corresponding t value. So, you took the t value from the students t table. This is another step. Now, from the t table, we get t is equal to 2.776. I just shown you how to pick up the t value with the help of two things, that is degrees of freedom and confidence interval. Step 4, calculate the confidence interval as Ci is equal to x bar, that is average, plus or minus t into s divided by root 10. In the present problem, s bar is equal to 9.92 plus or minus 2.76 into 0.12 is the standard deviation divided by root n, root 10 is equal to root of 5, and you will get the confidence interval as 9.92 plus or minus 0.15 ppm. Now, we have to interpret this result. Thus, there is 95% confidence that the true value of the concentration of a solute in the solution lies in the range of 9.92 plus 0.15 and 9.92 minus 0.15. So, that lies in the range of 9.77 to 10.07 ppm. Hope you got the point. This 9.77 is 9.92 minus 0.15 and this 10.07 means it is 9.92 plus 0.15. This is the interpretation of the result. Now, we are discussing some problems associated with the topics we discussed so far. First of all, an MCQ based on the concept we learned, which is associated with the coefficient of variation. This is the question in front of you. What does the coefficient of variation CV measures in analytical chemistry? These are the 4 options in front of you: accuracy of a method, relative precision of data, confidence interval width, method of robustness. On careful analysis of the 4 options, we can arrive at the final result like this. Option B is your answer, relative precision of data. So, coefficient of variation measures relative precision of data. Now, this is the second question. If the mean of a data set is 50 and the standard deviation is 5, what is the coefficient of variation? These are the options. Option A 5%, option B 10%, C 50%, option D 0.1%. It is very easy to calculate the coefficient of variation provided you are having standard deviation as well as the mean of the sample directly given in the problem. So, you have to find out RSD first. In order to calculate RSD, you have to divide standard deviation with x bar. Just to multiply with 100 to get RSD percentage. RSD percentage is known as coefficient of variation. So, the answer to the problem is 10 percentage, that is CV is equal to RSD percentage. RSD is equal to 5 by 50, just to multiply with 100 and you are getting 10 percentage. So, your answer is option B. Now, we can discuss another problem which is associated with variance. It is a very simple problem, a direct problem. Variance is the square of which of the following? There are 4 options: mean, standard deviation, median and range. It is very well clear that variance is the square of the standard deviation. You know there are 2 kinds of standard deviation, population as well as sample. So, there are 2 kinds of variance, that is population variance and sample variance, both are squares. So, the answer to the present problem is option B, that is a standard deviation, that is variance is the square of standard deviation. Moving on to next problem. In a data set with the variance of 4 parts per million square, what is the standard deviation? These are the options: 2 ppm, 4 ppm, 8 ppm and 16 ppm. The variance is given and what is the standard deviation, which is a direct problem. You know variance is the square of the standard deviation. So, variance is equal to 4. So, you have to take the square root of the variance. Square root of 4, that is equal to 2. So, your answer is option A, 2 ppm. Very well clear that the standard deviation is the square root of variance. This is another problem. Confidence interval express which of the following? These are the options: the exact value of a measurement, the range of possible errors in an experiment, the range where the true value lies with a given confidence, the robustness of a method. These are the options in front of you. On careful analysis, we will get the right answer as option C, the range where the true value lies with a given confidence. A confidence interval becomes narrower when the confidence level is increased, the sample size is decreased, the sample size is increased, the variance is increased. The answer is also shown here. The sample size is increased. As the sample size n increases, the standard error, which is notated as s by root n, decreases, leading to narrower confidence interval. So, as the sample size increases, then it leads to narrower confidence interval. That is, in order to narrow the confidence interval, you have to increase the sample size. That all about this module. Have a very nice learning experience. Thank you.